Hello everyone and welcome to another lesson. In this video, we will be discussing the industrial stoichiometry for nitrogen industries, particularly ammonia and nitric acid production. We will be discussing heavily on the computational side of the industrial stoichiometry. So let's begin. Let us first discuss the base ingredient for both ammonia and nitric acid, and that is nitrogen. Nitrogen is largely present in the atmosphere as a stable diatomic molecule. Basically, it is free. You just have to extract it from the air. However, diatomic nitrogen is very stable, and as such, it can only be oxidized at very high temperatures. This naturally happens in coal-fired power plants or in the engine of motor vehicles because the oxidant used in those cases is oxygen coming from air, but air also contains nitrogen. And at the high temperatures sustained during combustion, oxides of nitrogen are formed in small amounts. In industrial processes, when we want to obtain oxides of nitrogen, the direct oxidation of diatomic nitrogen is very unsustainable. As such, we have to convert diatomic nitrogen into another form before we can obtain oxides of nitrogen. In its pure elemental form, nitrogen can be used for a variety of purposes. Its primary use is in cryogenics in the form of liquid nitrogen. It is used to preserve a host of biological specimens as well as cool down metals and alloys to exploit their superconductive properties. Another use of diatomic nitrogen include modified atmospheres wherein we can mix nitrogen with pure oxygen in order for us to have a different ratio of nitrogen to oxygen. This can be useful in environments wherein we are avoiding explosions, and as such, nitrogen there is used as a diluent because nitrogen is non-combustible. We can easily control the percentage of oxygen in the modified atmosphere simply by adding more nitrogen. And in general, pure nitrogen is available as an industrial gas stored in metal cylinders that can be used for a variety of purposes such as what was mentioned earlier. Pure nitrogen is also mostly used in lab settings wherein nitrogen can be used as a sparger to remove some dissolved oxygen or other dissolved gases in liquids, and it is also used as an inert gas either as a diluent or as a blanket, again to prevent explosions or unwanted reactions. Our focus in this video is not for pure nitrogen but for its two most widely used compounds. Let's start with ammonia. Ammonia, with chemical symbol NH3 or one nitrogen atom combined with three hydrogen atoms, is widely used as a precursor to fertilizers and agrochemicals. Basically, ammonia is the backbone of the fertilizer industry. Ammonia is also used in cleaning products. It is present in a dilute aqueous solution. As a refrigerant, ammonia is used in industrial ice production. Water purification, ammonia is sometimes used as a disinfectant, and manufacture of other industrial chemicals in which ammonia is a precursor, such as dyes, plastics, explosives, and many more substances. In the industrial production of ammonia, it is mainly produced through the Haber process, in which the main reaction is depicted here. It is simply the combination of one molecule of nitrogen gas and three molecules of hydrogen gas to form two molecules of ammonia gas. And if you will notice, this chemical equation is written as a reversible reaction. That is because the formation of ammonia is very much limited by equilibrium. Case in point, this reaction will not happen at appreciable amounts at room temperature. Basically, we have to give this high temperatures and high pressure in order for us to overcome the limitations set by equilibrium for us to obtain an appreciable amount of ammonia. As I have mentioned earlier, diatomic nitrogen is a very stable molecule. As such, it is not easily converted into its compounds. The Haber process, or the production of ammonia, is one of our most economical and most practical ways of converting elemental nitrogen into one of its compounds. Next, let us talk about nitric acid. Nitric acid is another important nitrogen chemical that is derived from ammonia. Nitric acid is a very strong acid and it is also a strong oxidizing agent. It is the combination of these two properties that gives nitric acid a very distinct niche use in the cleaning of surfaces and in the extraction of metals from their ores. In the industry, nitric acid is mainly produced for use in the textile and fertilizer industries. In the fertilizer industry, nitric acid is prized for containing the nitrates ion, which is an ion that can be readily absorbed by plants to be used as their source of nitrogen. In the olden days, nitric acid was referred to as aqua fortis. You might encounter some old text or some old references that states that they use aqua fortis, and now you know that that is nitric acid. Nitric acid is used extensively in the metallurgy of relatively inert metals such as platinum, gold, rare earth metals, and other metals that are not dissolved by common acids such as hydrochloric acid or sulfuric acid. However, the use of nitric acid in metallurgy is often in the form of aqua regia. Aqua regia is a mixture of nitric acid and hydrochloric acid with a ratio of 3:1. That is 3 parts hydrochloric acid and 1 part nitric acid. This combination of two strong acids along with the oxidizing power of nitric acid is more than enough to convert almost all metals into their ionic states. The industrial production of nitric acid is mainly carried out by the reaction of water with nitrogen dioxide through the Ostwald process. This is the main reaction for the absorption of nitric dioxide to water in the Ostwald process, forming nitric acid and nitrogen monoxide. Nitrogen monoxide is typically recycled to be converted back to nitrogen dioxide, and that allows us to use a large part of the nitrogen. Although in some cases, if the fraction of the nitrogen monoxide in the absorber gas is low, then we can elect to no longer recycle the stream. The number one limitation of the Ostwald process is that nitrogen dioxide cannot be economically produced by the direct oxidation of nitrogen gas because of the high temperatures involved. What we mean in this statement is that nitrogen dioxide cannot be easily obtained by burning nitrogen with oxygen. As I have mentioned earlier, this only happens at high temperatures such as in coal-fired power plants and in the engine of motor vehicles. And even in those cases, the fraction of nitrogen dioxide produced is very small, and that cannot be utilized in the industrial production of nitric acid. Instead of combusting pure elemental nitrogen, we instead oxidize or combust ammonia. So from ammonia, we burn that to produce nitrogen dioxide. We let that be absorbed by water to produce nitric oxide. So in a way, one of the precursors for nitric acid production is actually ammonia and not pure elemental nitrogen. Since ammonia is a crucial part of the production of nitric acid, in fact, it is the most important feed to the process, we need to discuss how is ammonia produced. As mentioned earlier, the industrial production of ammonia is carried through the Haber process, and this is a simplified block flow diagram of the Haber process. This will allow us to perform material balance calculations for the production of ammonia. We have the two main units in the Haber process, the reactor and the condenser and separator. The purpose of the reactor is to convert nitrogen and hydrogen to ammonia, and the purpose of the condenser is to separate ammonia from the reaction mixture. That is because the nitrogen and hydrogen that are unreacted is recycled back to it with the provision of the purge stream. The purpose of the purge stream here is to prevent the accumulation of argon. Argon is typically found in low concentrations as an impurity in nitrogen used for the Haber process. If we will not include a purge stream in the Haber process, the argon will just accumulate in our system because it is not passed through the product, which is pure ammonia. So that's the importance of the purge stream. Our diagram also contains a mixing point and a splitting point. The mixing point is found here. This is the point where the fresh feed is mixed with the recycled feed in order to obtain the mixed feed. The mixed feed is the one being fed directly to the reactor. The splitting point is found over here. This is where the effluent of the condenser/separator is separated into the purge stream and the recycle stream. One of the special properties of the splitting point is that this is just a physical splitting. There is no separation of components involved in the splitting point. As such, the composition of the purge stream G is equal to the composition of the recycle stream R because they come from the same splitting point. And their composition is the same as the effluent of the condenser. Take note that I am saying compositions are equal but not their flow rates. We can also perform material balances on the splitting point and on the mixing point depending on what is asked in the problem. To simplify our calculations, most often the product A here consists of pure ammonia because ammonia is the only component in the reaction mixture that can be condensed at a reasonable temperature and pressure. Hydrogen, nitrogen, and argon all have very low boiling points, and as such, there is no simple way of liquefying them in the condenser. If you take a look at our reactor, I have here posted some typical values of the operating temperature and pressure of the reactor in the Haber process. Temperatures usually range between 400 and 450 degrees Celsius, while the pressure is around 200 atmospheres. That is a very high pressure, and that is important in obtaining a reasonable amount of conversion from nitrogen and hydrogen to ammonia. Let us try to illustrate the material balances of the Haber process by solving an example. In a Haber process plant, pure ammonia is produced as a product and a purge stream is provided. The fresh feed to the process is supplied at 150 moles per hour and contains 75.10% hydrogen, 24.65% nitrogen, and the balance is argon. The mixed feed contains 79.72% hydrogen. The overall conversion of the limiting reactants was found to be 0.9958 or 99.58%, and the purge stream contains 5.75% nitrogen and 80.50% hydrogen. We want to determine the product's flow rate in moles per hour, the rates of recycle and purge also in moles per hour, and the single pass conversion of the limiting reactant. What's important to take note here is that in the problem, we are given a value of the conversion, that's 99.58%, but this is the overall conversion of the limiting reactant. The single pass conversion is a different value from the overall conversion. We will illustrate that later. But first, let us draw our diagram and complete our given. Welcome back, and in here we have our block flow diagram filled out with the given from the problem. And as you noticed, I also specified our overall boundary. The specification of the overall boundary simplifies the first steps of our solution for this problem. Let us first answer the first required, and that is, what is the product flow rate? In this case, our product is stream A, and that is the pure ammonia stream. But before we do that, let us first complete the compositions of the feed and of the purge stream. If you notice in the problem, it was mentioned that the balance of the feed stream is argon. If you take a look at the compositions of the feed stream, 75.1 plus 24.65% is not equal to 100%. That means that the remaining 0.25% in this case is argon. So we need to specify that argon in the feed is 0.25%. The same thing has to be done on the purge stream. If you notice, 80.5% plus 5.72% is also not equal to 100%. It's only 86.22%. That means that the remaining 100 minus 88.62, which is 13.78%, is our argon in the purge stream. That step is very crucial in any problem involving the Haber process. You need to make sure that all of your streams have a total of 100%. In the filling up of the remaining components of the purge stream, our main assumption is that there is no ammonia in the purge stream. Or if there is ammonia, its concentration is very, very small such that we can consider it negligible. Now we can build our solution and answer what is the product flow rate. We will start our solution with an overall material balance or OMB. For our overall boundary, we have F is equal to A plus G. However, there is a problem with this equation. This is only true if all of the values here are in mass units. That is because the overall material balance is a mass balance. It is not a mole balance. For reactive systems, we cannot use the OMB in terms of mole units because the number of moles can vary from the reactants to the products. As such, we will not be using our OMB here. What we can do instead is to make use of the inert substance, and that is argon. We can use argon in a mole balance in the same sense as we can use it in a mass balance because argon is not reacting in this system. That means that I can write the following relationship, that is 0.0025 multiplied by F is equal to 0.1378 multiplied by G as our argon balance. We are not violating any rules here again because argon is not reacting in this process. Since the flow rate of the feed is given in this case, we can directly solve for the flow rate of the purge stream G. That is simply 0.0025 multiplied by 150 moles per hour divided by 0.1378. Our purge stream has a flow rate of 2.72 moles per hour. Now that we know the value of the purge stream, we also know the flow rate of the feed stream. Can we now determine the flow rate of the product stream using our OMB? We still cannot use this because we are using mole units. What we can do now is we can perform atomic balances in order to find out the molar flow rate of our product. And in this case, we can easily do that with a nitrogen balance. Our nitrogen balance is written as 2 times 0.2465 times F. This is the number of moles of nitrogen in the feed. That is equal to the number of moles of nitrogen in the ammonia stream. That is simply written as A. A is the molar flow rate of the product stream, and it just so happens that it is pure ammonia. And also in the product side, we have to add the contribution of the nitrogen in the purge stream. So that is plus 2 times 0.0572. That is 5.72% of the purge stream is nitrogen. And as you can see, just by using the nitrogen atomic balance, we can now solve for the value of the molar flow rate of the product stream, A. That is 2 times 0.2465 times the feed stream, 150 moles per hour, minus 2 times 0.0572 times the flow rate of the purge stream, 2.72. The flow rate of our product stream is 73.64 moles per hour. And that is how you perform the overall balances for the Haber process. For the determination of the product flow rate, alternatively, you can also perform the hydrogen balance. That is because ammonia also contains hydrogen, and you would still arrive with the same answer of the product flow rate whether you use the nitrogen or hydrogen balance. Let's proceed to the next unknown. The next question asks us to solve for the rate of recycle and purge. In our previous solution, we were able to solve for the value of the flow rate of the purge stream, so that is already taken care of. We just need to solve for the flow rate of the recycle stream. Now, where do we start? If you take a look at our diagram, the recycle stream is connected to it's either the mixing point or the splitting point. In terms of our balances, we cannot use the splitting point because we do not know anything about the reactor effluent stream E, and that is a direct contributor to the splitting point. However, if you take a look at the mixing point, we know everything there is to know about the feed stream, and we know the hydrogen content of the mixed feed stream. For the recycle stream, as I have mentioned earlier, this has the same composition as our purge stream, so we know that as well. So we can get something by performing the balance at the mixed feed. My point is, we will be able to get the flow rate of the recycle stream if we perform the balance on the mixing point instead of the splitting point. So let's perform the balance at the mixing point. Keep in mind that the mixing point is a physical process. It's just a mixing process. Therefore, there is no chemical reaction involved in the mixing point. In this case, we can use the OMB, but we will have to rename it as the overall mole balance. Again, I would reiterate you can only use the overall mole balance for processes that do not involve chemical reactions, such as the mixing point and the splitting point. Our OMB in this case is written as F, or the fresh feed, plus R, or the recycled feed, is equal to M, or the mixed feed. We know the flow rate of the fresh feed, so we can rewrite this as 150 moles per hour for the fresh feed is equal to mixed feed minus recycled feed. I'm calling this equation number 1. In our equation 1, we have two unknowns, that is M and R. Therefore, we still need another equation in order for us to determine their values. Our second equation would come from a component balance. It's either hydrogen, nitrogen, or argon. But if you take a look at our given, we are only given the hydrogen concentration or the mole percent of hydrogen for all streams. For the mixed feed, that is 79.72%. For the fresh feed, it's also given. And for the recycle stream, since it has the same composition as the purge stream, we can also use the composition of the purge stream to represent the composition of the recycle stream in this case. If we will write a hydrogen balance, that would be on the fresh feed 0.751 F plus on the recycle feed 0.805 R. And finally on the mixed feed 0.7972 M. Rearranging, this becomes 0.751 times 150, this is the flow rate of the feed, is equal to 0.7972 M minus 0.805 R. This is our equation number 2. The reason why I have written the two equations in this particular form is that now we can represent the equations as x plus y is equal to a constant c. This makes it easier for us when solving two equations with two unknowns. Our mixed feed is our variable x, our recycle feed is our variable y. So let's try to solve that in our calculator. That is mode 5.1. This is two equations, two unknowns. A is the coefficient of x, B is the coefficient of y, and C is the constant. For our first equation, the coefficients are 1, -1, and 150. For our second equation, the coefficients are 0.7972. For B, that is -0.805. And the constant is 0.751 times 150. Therefore, we say, solving both equations 1 and 2 simultaneously, we were able to solve for the mixed feed, which is 1038.46 moles per hour. And the recycle stream is our variable y, that is 888.46 moles per hour. Thus, we were able to solve for the flow rates of the recycle stream. Okay, let's proceed to the last unknown. For the final question, we are asked to solve for the single pass conversion of the limiting reactant. In this case, you can check that our limiting reactant is nitrogen. For us to solve this problem, we have to make a distinction between the overall conversion and the single pass conversion. The value that was given earlier, 99.58% conversion, is the overall conversion. And this applies to our overall boundary. This means that of all the nitrogen entering in the fresh feed stream, 99.58% becomes ammonia, while the remaining 0.42%, the balance of the conversion, exits as nitrogen in the purge stream. We can consider this nitrogen in the purge stream as our losses in the process. Now, what about the single pass conversion? The single pass conversion only pertains to the reactor of the system. Thus, for this last part of our solution, we will only be considering the reactor. If you take a look at our reactor, the input to this process is the mixed feed containing hydrogen, nitrogen, and argon, and the outlet to this unit is the effluent stream labeled as capital letter E. Now, what does the effluent contain? Of course, we would expect that since the conversion is not 100%, there would be remnants of unreacted reactants in the effluent. That is, we expect nitrogen, hydrogen, and argon in the effluent stream. But since the effluent stream is the exit of the reactor unit, we would also expect to have a product in the effluent stream. And our product is ammonia. Now, before we figure out the amounts of the components of the effluent stream, let us define what is the single pass conversion. The single pass conversion, that is F1, is equal to the number of moles reacted divided by the number of moles fed. Both of these parameters pertain to the limiting reactants. In this case, our limiting reactant is nitrogen. As such, the numerator of the single pass conversion pertains to the number of moles of nitrogen reacted, while the denominator pertains to the number of moles nitrogen in the feed to the reactor. That is the number of moles of nitrogen in the mixed feed. Let us first look for the number of moles of nitrogen reacted. If you take a look at our diagram, you would see that the only source of ammonia in the system is the ammonia that is present in the effluent of the reactor. As such, we can say that all of this ammonia, 73.64 moles per hour, is also the flow rate of ammonia in the effluent stream. So let me write that ammonia here is 73.64 moles per hour. This means that for every hour, there are 73.64 moles of ammonia being produced in the reactor. And the number of moles of ammonia being produced can be related to the number of moles of nitrogen being reacted. Of course, that is the case because nitrogen is the limiting reactant. We only need to perform stoichiometry to determine the number of moles of nitrogen reacted in the reactor. That is equal to 73.64 moles of ammonia generated, and for every 2 moles of ammonia generated, there is 1 mole of nitrogen gas consumed. Where did I get this conversion factor? This comes from the balanced overall reaction of the system. That is N2 plus 3H2 yields 2NH3. It's just simple stoichiometry. That means that the number of moles of nitrogen reacted is 73.64 divided by 2. That is 36.82 moles. We now have figured out the numerator of our single pass conversion. How about the denominator? The number of moles of nitrogen in the mixed feed can be determined by performing another component balance in the mixing point. If you take a look at the mixing point, it involves the feed, the mixed feed, and the recycle stream. Therefore, we can say that the number of moles of nitrogen in the mixed feed is equal to the number of moles of nitrogen in the fresh feed plus the number of moles of nitrogen in the recycle stream. Since we now have all of these values, we can simply calculate this as 0.2465 times F plus 0.0572 R. Remember that the recycle stream and the purge stream have the same composition. Substituting, that is 0.2465 times feed 150 plus 0.0572 times the recycle stream, that is 888.46. We have 87.79 moles of nitrogen in the mixed feed. Now that we have our numerator and denominator values, we simply divide them to get the single pass conversion. 36.82 divided by 87.79, our single pass conversion is equal to 0.4194 or 41.94%. And that is how you perform the material balances for the Haber process. You just have to remember some of the few techniques being used in the Haber process to simplify our calculations. and those assumptions were outlined throughout our solutions. The Ostwald process, or the production of nitric acid coming from the combustion of ammonia, will be discussed in the next video. That's it for this video. Thank you for listening, and as always, keep safe.